Much better. Alrighty, so I'll go back to presenting. Okay. And go back here. Alrighty. Well, we'll try this again. Yeah, exams coming in, I hope. And Thursday, I suppose you heard my phone ringing there right at the beginning of class. I did not answer it, but it may impact Thursday's class. So right now, and I'll maybe send out an email right after class, if I can figure out from the message whatever they leave. But I have an appointment on Thursday, but I don't know when. And so it probably, my guess is, it's probably going to mean that we can't meet. And so we'll get over it if that's the case, and I'll just send that out. But I'll let you know as soon as I can. I think in many ways what I had planned for this week before I even knew about this other was really just trying to do a little project work and get caught up on that a little bit. We probably won't get totally caught up by the end of the semester, but I think we're pretty well on our way. I've got, what I'm going to do today is talk about what we're going to do with Chapter 6, which is just a project, okay? Because Chapter 6 was never really meant to be an in-depth thing for this class anyway, because it's differential equations, and we have a whole semester on differential equations if one wants to take that. And but I think it's a good topic for an introductory calculus class. And so we'll do just because we're kind of behind on some things anyway, plus the way the semester was compressed even a bit. This week we'll work on this project. Once I get it finished, I'm going to go through the first 2 pages of it today to give you an idea what's kind of going on, and I'll try to get another short project out there, and try to today just kind of show you where this one's coming from and going and all that. Anybody have any questions on anything right now that need to be addressed? No, guess not. Okay. All right. Well, so we are looking at, in Chapter 6, solving differential equations, and they go through various techniques, some nice graphical numerical things that are good, and they kind of sit on top of the tangent line idea. We've seen that a little bit way back in Chapter P, I think, in our first project when we looked at growth. And this project kind of looks back at growth again. And they also mention a particular technique, and that's the one thing we're going to do in this project, is this one technique that is typically the kind of the first technique one learns in a differential equations class. And it's a nice application of integration by substitution. And so it all fits together that way. I'm not going to... Well, that's weird. That's still on freeze. Well, you all see what's going on. I see now. I didn't expect to look over there and see that. Okay. So, okay. I'm going to go over the first couple pages. I'm just going to show real quick here. You know, so they look very. It looks very mathy. So the first page of this is the technique. Okay, what's going on with the technique, and then the second page is an example. And a very straightforward, simple example, but an example nonetheless that we can get and take a look at. And then it goes into the part 2, which is going to be where we actually do stuff. And notice, you know, right now I don't have very much of it. It just, you know, but it does start out in part 2 of module 1. You know, we did this, and so it also kind of builds on that stuff. So with that, I will go back to the Blackboard view and look at this. So we want to solve a differential equation, and most generally a first order. So hopefully you're starting to get this idea of order. So first order usually means first derivative, second order, second derivative, that kind of thing. So a first order differential equation, typically a nice one, a linear one or something like that, or one we can tend to solve, you know, is going to start with just dx dt. You know, here's the derivative part on the left-hand side of the equation. And on the right-hand side, typically you'd see this with an f, but because of the way I start out our separation of variables, I'm going to call it an h. Is that on the right-hand side, you would tend to see then something involving x's and t's. And that's all this is saying, is that typically, you know, you'd have the derivative or the rate of change of x as a function of t. Well, it's, you know, it's it's complicated, right? So, right, it involves a bunch of x's and t's, and yeah, it may be complicated or it may not be so complicated. And so that is the kind of differential equation we're looking at. And then normally you'd be told that, you know, say, now it doesn't have to be 0. We're going to go ahead and use 0 just to make our life easier. And, you know, we're not going to dive into this that deeply. You know, that we're given some initial value somewhere. Typically, though, because differential equations like this tend to be about starting at some time and moving on, we'll just call that initial time times 0, whatever it is. You know, it could be 3 days in the future, but that's when I care about it, so we'll call that time 0. So that's what we want to solve, but we want to solve a very particular case. And we're going to look at this separation of variables idea. And we're able to do this if this right-hand side has a real specific form, and that is that we would have dx dt is equal to some g of t, so something only involving t, not x. Now constants, I don't care about constants, they can be all over the place, doesn't matter. But it only involves t. Now actually so far you've solved these differential equations. I'm going to add more to this, but you've solved these. So we know how to solve, this is just, you just do an antiderivative. Okay, so we know how to solve something that looks like that. Now, I say you just do an antiderivative. Well, if I don't know the antiderivative, I guess I'm stuck as far as a symbolic method. But then times something involving x. But you see, they're separate. They're separable by multiplication. I can think of these as two factors. One factor involving only t's and one factor involving only x's. Okay, and then we'd still have our initial condition. Okay, so that's what we want to solve. And actually, theoretically speaking, it depends on the antiderivatives and so forth, but theoretically speaking, piece of cake, this is easy. Okay, now, the reason it's easy is, well, I'm going to divide both sides by f of x. So when I divide both sides by f of x, I have 1 over f of x dx dt equals g of t. Now those are both functions of t, okay, because x is a function of t, it's pretty much implied here. Otherwise, why would I ever take its derivative with respect to t if it wasn't a function of t, right? You know, so, and I guess even if it's a constant, well then its derivative would be 0. I could still do this. So, you know, x is some function of t, and the reason I'm going with x and t as opposed to y, say, and x is, again, typically with the stuff we're looking at, the independent variable is time. And so now we'll call it t. And so we have this x of t like this. Now, so here's a function of t, here's a function of t. They're the same function. It says so right there. Okay? They are exactly the same function. I don't know what the heck it is. That's the point, right? That's what I'm trying to figure out. But those two things are exactly the same function. Well, if they are exactly the same function of t, then I could integrate both sides with respect to t. Okay, so I do that, and they're going to be equal at least up to an arbitrary constant. So, any questions about that so far? I think it's pretty straightforward, right? You know, so I've got something that if I can see it this way, if I can write it that way, then certainly I could just divide both sides by whatever that f of x expression is. You know, put that function over there, and then I can take antiderivatives. Again, you know, it's, well, can I really? I don't know. We'll see. But theoretically, I can do it. It's a piece of cake. You know, I just, well, there it is. Now, what we notice here is actually, this is our integration by substitution. Right? This is the chain rule. I have f of x. Now, it says 1 over, but let's not get worried about that. I've got f of x, and then times the derivative of x with respect to t, and then the dt. Right? That's in our substitution stuff. That's how we substitute dx is dx dt dt. That's what we just got done doing with in chapter 4 with integration by substitution. You okay with that? That's what we did, right? We did that chain rule, and so we made that substitution. So with that substitution, then I now can write this as something that looks like something I might be able to do. So substituting that in, I get 1 over f of x dx is equal to g of t dt plus c. And see, just as I look at it, now, again, the 1 over f of x, I don't know what that's going to mean. We'll see in our example that it doesn't actually have to be scary whatsoever. It's just a symbol saying how we got there. I could rename it something else and call it like q of x dx instead of 1 over f of x. Okay, but it's just some function of x dx, antiderivative. Some function of t dt, antiderivative. And I've got my arbitrary constant to make sure that these two things are equal in the sense that, yeah, sure, I've got two antiderivatives. They may differ by a constant. Okay, so with that then, I do the antiderivatives. Now, and here's where we do see that this notation of an uppercase letter does not necessarily mean its derivative is the lowercase letter. Okay, because what I'm going to write over here is when I do that antiderivative, I get uppercase f of x. Well, I'll write it over here, but that's because I'm saying uppercase f prime is 1 over f. Okay, it's 1 over f, whatever that function is. Okay. It can be because there's nothing standard about the uppercase f and so forth. So I get this equals g of t plus our arbitrary constant. And so what I'm saying here is that, well, f prime of f of x is 1 over f of x, like that. Okay? And I can say that, right? Because I'm defining what things are. And g prime of t is little g of t. Okay, so I'm just using symbols to keep track of stuff. Okay, so there I have that. And that is an implicit solution. Okay, so see that's implicit in that, well, that could be like x squared, square root of x. Could be e to the x. Who knows what it is, right? Could be x sine x or something like that. I mean, it's something involving x, but probably not just x equals, right? So this is an implicit answer. Well, so the question is, can I get an explicit answer? Well, first, let's take care of our constant. So I get this answer, and remember that x of 0 is equal to x0. Well, putting that in here, substituting that in, I have that f of x0. Okay, now once I do that, that's a constant. Some number. I don't know what it is, but it's a number. Equals g of 0. Okay, because t is equal to 0. So when t is equal to 0, x is equal to x sub 0. And then plus c. So that means c is equal to f of x0 minus g of 0. Ha! Glad I'm doing this before I give it to you. I got a typo. Well, I tell you. Be nice if I was good with numbers. Okay. All right. So had this reversed in here. Yeah, it happens. Okay, so that's C, and so if I plug that in here, then f of x is equal to g of t plus f at x0 minus g of 0. Whatever, so that's our constant C, whatever that turns out to be. And now it's still implicit. Okay, but if F inverse exists, okay, if it's something I can take the inverse of, like if it's a square root, I can square both sides. That's not a problem. If it's an exponential, if it's e to the x, I can take the logarithm of both sides. If it's a logarithm, I can exponentiate both sides. I can get the inverse of it. So if I can do the inverse function, then my final answer is x equals f inverse of whatever g of t is, plus that constant, f at x0 minus g of 0. And there's my answer. Sort of every single time. I mean, if I can go through these calculations, I'll have an answer. I can tell you exactly what this function is that's related by this differential relationship. Okay, any questions on anything on that? Okay, so we'll do an example where, for one, we'll see that even though you write 1 over f of x, okay, because from the way we started things out, that's the way it's written. Well, actually, this might not be at all scary whatsoever. Maybe quite nice. And so, what I want to solve is dx dt is equal to 2t over x squared, where x of 0 is 3. Now see, as you look at this, what you see is that our g of t is 2t. Now there is some arbitrariness to some of this, right? So I'm going to say g of t is 2t. Well, I could have just said it was t. And then I could have said f of x was 2 over x squared. Okay, but I'm not going to. And the reason is that usually a constant like this, just when you do this method, it's better to just leave it over on the right-hand side and not worry about it. Just leave it with t, whatever is over there. So I have this, and then my f of x in this case is 1 over x squared, and that would give me g of t times f of x. Now, in practice, I don't really have to think about that being 1 over x squared. Pretty much what I do in practice, I look at this and I say, oh, can I separate it? Can I just multiply both sides of this by something involving x to get all x stuff over here and all the t stuff over there? And, if I multiply everything by x squared, I can do that. And so that's what I do. I multiply both sides by x squared, which, if you look at our notation, and so I'm dividing both sides by f of x. And so this becomes x squared dx dt equals 2t. And then, typically when students in a differential equations class, solve these things at first and do the separation of variables, often, actually what you'll see is from this step, what it looks like they did is they multiplied both sides by x squared. Yep, that's great. But then they often will leave out this step here, and they'll just write the integral part that involves the dx, and they'll have the dt over here, and they'll slap an integral sign there, and they'll have the dt there and the dx there. So what it sort of looks like is they multiplied both sides by x squared and multiplied both sides by dt and canceled it out. That's not really quite what happens. That's, it's the differential. It's actually a substitution going on. So the only dividing we did, or multiplying, was to get the x stuff over here. But this dx dt, it is one item. It always stays together unless we can do some sort of substitution. And what we're able to do at this point is not that we're multiplying both sides by dt. No, that's not at all what we're doing. We're integrating both sides with respect to t. That's what we're doing. And by doing that, those dt's appear, and we're able to do that substitution. So, our next step is this x squared dx dt. Dt equals the integral of 2t dt. And then I'll go ahead and put my arbitrary constant out there. Again, there are some things, if you're just solving these things, do I need that there right now? Nah, not really. Well, I've still got those integral signs on both sides. But as soon as I get rid of one integral sign, it might be better to have a plus c there. And definitely by the time I've done all my antiderivatives, I need to have an arbitrary constant there to truly make it equal. Okay, so we have this. But again, that's just dx. That's our substitution. So this is x squared dx and 2t dt plus c. And see, now these look easy. Well, they look easy because they're easy antiderivatives. Obviously, you could end up with functions here, on this right-hand side that you don't know how to do the antiderivative. Sure, you get stuck there. Now, generally, if you can separate the variables, if you can see how they're separated, you don't get stuck there. It's possible that you could not realize something's separable when it actually is. So you could get stuck there where you don't have to be stuck, in that, if you did the right algebra, you could do it. And there are actually some cases where you can do a variable substitution, do a change of variables of something, not as in this sort of substitution here, but a different change of variables. And you can take something that's not separable in the way you had it formed, but make the substitution, and then all of a sudden it becomes separable. So there are lots of techniques. People have been working on these things for years and years and years, long before we even really had names like calculus and all that. They've been working on problems such as this. So there are some really, really slick ways to solve things. I can never remember most of them, but there are some really slick things one can do. Okay, so we've got these antiderivatives. We've already got our arbitrary constant in there. So here I get x cubed over 3 equals t squared, and then plus our arbitrary constant. And so there's our implicit solution. Well, not fully. We don't know what C is yet. But I've got an implicit solution. However, it is one I can get an explicit solution for, because an x cubed I can take the cube root of. Now you got to be careful with x squared. X squared does not necessarily have an inverse. It all depends on the values that go into it, right? Because x squared U-shaped, are you on the left side or the right side? Or when you take the square root, you get a plus minus. But with x cubed, yeah, I can do that. I can take the cube root of both sides. So we have this. So the next thing I want to do, and again, you can do some of this in a different order. Like I could multiply both sides by 3, and then take the cube root of both sides, and then I could find C. Usually, but not always, usually it's probably easier to find C at this stage. However, actually, the first problem you'll do on your project is probably a little easier to do all the work first and then find C. That'll be in the project, but those are small things. Okay, so we want to find C. Well, remember that x of 0 is 3, and so that means we get 3 cubed over 3 when t is 0, and so we have C there, and so we see that C equals 9. Okay, all right, because 3 cubed over 3 is just 3 squared, and then equals 0 plus C. So C is 9. So that means we have x cubed. Now I'm going to go ahead and multiply everything by 3 to at least just get it as x cubed. And so then we have our 3t squared plus, now we've got 3c. So we end up with a 27 there. And there's an implicit function. But what's nice is x cubed has the inverse of the cube root. And so we can write as our final solution 3t squared plus 27 to the 1/3 power, or we could do the radical sign with a little 3 in there for the cube root. And there's our solution. So there's an example now, but it's not a bad idea. We can check our solution. I'm going to leave that part up here right now. But we're going to check our solution by taking its derivative. And we can also check, is the initial condition correct, right? We have x of 0 is 3. It should be. I mean, we made it that way, but, just to check, x of 0 is equal to 3 times 0 squared plus 27 all to the 1/3. So that's 27 all to the 1/3, which is 3. So that part does work. And then, okay, how about the derivative? So I want to take the derivative of this thing. So dx dt is equal to, well, if I want to take the derivative of this thing, I've got a chain rule going on. Bring the 1/3 down. So I get 1/3 times all that stuff on the inside to the negative 2/3. Like that. And so that stuff inside is 3t squared plus 27. And then times that derivative, 3t squared. So that would be 6t, and of course the 27 is 0. So we get that. Well, the 1/3 6t, that's nice. That's 2t. So this is equal to 2t, and then times, well, this is to a negative exponent, so we can make that 1 over. And that's 3t squared plus 27. Now, the 2/3 power, right, I can write that as the 1/3 power squared. Right, so this is the 1/3 power, and then put on the outside of that I'll square it. And the reason I wrote it that way was to see that, what's x? That? Oh, well, that's what I have inside the square brackets. That's x. And so I can write this as 2t over x squared, which is what we started with. Okay, so it really does work. Okay, and that's an example. And it was a particularly nice one, sort of, in that, when we moved that x squared over here to the right, we got a really nice antiderivative to work with, integral, indefinite integral there. Okay, now, the rest of the project, it will start off with us actually showing our answer from module 1. Okay, and I can do that for you. Because it's not a big deal here. I'll kind of give you much of the steps anyway in the project. But remember, in module 1, one of our things that we looked at was something that looked like that, and this was population growth. Now, we started it as delta P over delta T, but then we said, well, if you do this calculus thing and make it really, really small, then you get this differential equation of dP over dt. And we found the answer. The answer to this was e to the kt, okay, times some arbitrary constant. Well, so as you look at it, well, how does that work? Well, look, there's my function of t. It's just a constant, but I'm going to leave it on the right-hand side. And there's my function of p that I can separate out and divide both sides by. And so this I can write as 1 over p dp dt is equal to k. And then I can integrate both sides with respect to t. So I'm just following that same method. So I integrate this, and I'll put it here. 1 over p dp dt equals antiderivative kt. K dt. And we'll end up with an arbitrary constant out here. Now, so here, natural logarithm, right? Well, I'll go ahead and do that next thing where I write it this way. Now, do I really have to write that step and this step? No, not really. I mean, they're saying the same thing, and then once I get that, I could either write this step or I could write that step. But here's our k dt plus our arbitrary constant. And so now we get natural logarithm of the absolute value of p equals KT plus C. Now, that absolute value actually is quite important to begin with, because it could be that for whatever reason you're going to deal with negative numbers, but probably not, because you're talking about populations. So it's often the case that if you get sloppy and forget those absolute values and you're truly modeling something real, you'll probably be saved from your own sloppiness, because everything's supposed to be positive anyway. But you never know. I mean, I've run into a couple cases where you were actually working with something that became negative. And so you have to be a bit careful. But so now here's a case where it might be a little more enlightening in some ways to not figure out what C is first. Now we can't, because I never gave us an initial condition. So I don't know what it is. All right. So it's kind of there. Well, natural log, it has an inverse, right? The exponential function. So this is, if I exponentiate both sides, I get the absolute value of P is equal to e to the KT plus C. Now, on something like this, this is where we usually notice, oh, well, you know, this is exponential, so if I'm adding two exponents up there, I could write this as e to the KT times e to the C, and that itself is just an arbitrary constant. And so I'm going to rename it. Now, I could just call it C. When I took differential equations, everything was just a C. That's really bad form, but I don't know, the teacher, that's how we were taught, and we just went at it, you know. So we would just replace this e to the C with a C. Not the best form. And in this case, actually, hey, since we're talking about P and all that, actually, a good thing to replace e to the C with here is the letter P0, well, two things, P0. So I'm going to call it P0 e to the KT. So all I did was I renamed this. Now the reason I renamed it is, notice if t equals 0, e to the KT is 1. Okay, so if I did come back here and say, oh, by the way, P of 0 is P0, yeah, that's exactly what it would be. Okay, so exponential functions are kind of a case where it's really nice to think of your constant this way instead of, you know, there. Just works out nicer to look at it that way. Not that, you know, I mean, you could come up with a number here. It would be actually the natural log of this P0. Okay, but this is much better. Okay, this is your initial population at time 0. That's a nice number to have. Right? So there we have it. Now, if P0 is greater than 0, right, because e to the KT is always greater than 0. Exponential function is always greater than 0. So if P0 is greater than 0, oh, well then I can drop the absolute values and I get P equal P0 e to the KT. And there's population growth. Okay, well that's pretty good. That puts us out of time. Again, I would say chances are highly likely that we will not be in class on Thursday. But as we're just kind of working on this project, and I've given you quite a bit of it here, I think you're going to be fine with that, and I'm going to try to get you another one started later in the week, kind of going back and hitting some things we missed as far as projects. But where we're going with this is I found a nice article on tumor growth. Okay, so I've been trying to hit a lot of biological type of applications, and I found something on tumor growth that uses a little bit more complicated differential equation than this to model it. But we can solve that differential equation by substitution. It took me a minute to see that. I mean, so it's kind of nice when you're doing stuff that's a little harder. I mean, at least, you're doing real stuff that other people have worked on. And, but anyway, they start by mentioning this model for tumor growth, and it kind of is lacking because it assumes it never would die, ever, right? You just turn into a bigger and bigger tumor or something. And so that's a bad model. But then they introduce some other ideas that make it a more complicated model, but we can still solve it basically this way. And so that's what we're going to do for the project, solve that differential equation and look at its graph and kind of play with it a little bit. All right, so I might see you on Thursday, but I'm guessing not.